Hello everyone, my name is Fatma and today my colleague Hasan and I will be presenting our research of energy impact analysis of select passive architectural techniques on a villa in Dubai. In this presentation, we will introduce our research followed by the weather and site survey. Then, we will discuss our methodology and literature review. And finally, we will discuss our results and conclusion. The intention of this research is to explore the evolution of sustainable passive architectural practices used in residential villa design over time, as well as the impact evaluation of various passive architectural strategies aimed at reducing the cooling consumption of residential dwelling. With this aim, we will start with analyzing the various sustainable strategies which were employed historically. Then we will simulate the villa under study by applying the current green building codes to correctly capture the present conditions. And finally, we will carry out the experimentations on selected architectural characteristics and quantify their effect on the cooling. As a result, we shall obtain relationships between the various building characteristics versus cooling consumption and maximum possible cooling consumption savings, especially in the case of sustainable city villa. The UAE is known for its harsh hot climate. Almost all the cities of the Emirates are coastal cities. Dubai has mild winters and hot, humid summers. Let's start by giving a brief site overview. The chosen villa is located in the sustainable city in Dubai. It's a 46 hectares property that was developed in 2015. That was modeled to be the first functioning net zero energy city in Dubai. This development is 18 miles away from the hustle of the city, located on Al Qudra Road. The chosen building is a 4-bedroom villa with a courtyard. Its total built-up area is 250 square meters with a rooftop livable area of 133 square meters. It has facilities such as solar power plant, a small garden, and a golf cart parking. The entire research has been divided into 3 thematic areas: past, present, and future, to understand the progression of practices and formulate lessons learned from the past and provide insights for the future. The research begins with a detailed literature review to gain an understanding of the historically applicable passive architectural techniques used in the construction of residential dwellings in the city. The literature review will also cover the current codes in effect in Dubai. Based on the literature, we will build an interpretation of the past and, as a result, choose passive architectural techniques that can be tested. To better understand the current situation, an actual villa was simulated using Dubai Green Building regulations. This will aid in comprehending the current patterns of energy use. To ensure that the current case is in the active of real-world conditions, the device mode will be adjusted and validated against the villa actual consumption. To make a future case, we first simulate the villa using Al-Safat Platinum Code to identify overall energy savings with respect to DGBR, and then experiment on improving the defined passive architectural elements. During the experiments, we created a relationship between cooling consumption and various configurations in order to determine the maximum scope of environment for certain architectural elements. To model the energy usage of typical Dubai villa under various building envelope configurations, the IESVA energy modeling software is used. The simulations also tested individual envelope components such as walls, roofs, and glazing. Additionally, the last design optimal configuration would be simulated. This ideal arrangement would include the most of the elements which were already incorporated in the computer models. Lifestyle, climate, and available building materials are major influences in the architectural style of traditional houses in the UAE. The earliest forms of houses in the past are tents. The Bedouin people moved a lot in their search for water and food, and so they needed a moving house. Usually the tent would be made of black wool, allowing air to enter through the small spaces between the wool and create a cooler air inside. Then moving on to Al-Arish homes, they were airy in summer as they allowed ventilation because they are made from palm fronds. In addition, moistened palm fronds were placed on the roof to cool the interior of the space. Palm trees were commonly used as they are a local resource. Lastly are the kola rag houses. These types of houses were mainly seen in the coastal areas of the Emirates. They were constructed using limestone and coral material. Coral rags had great characteristics to be used for making houses. Internal pores of the coral act as an insulating material and help in regulating the day and night temperatures within the house. According to the modern civil engineers, the coral walls were a sort of a breathing wall, as they expanded due to heat during daytime and contracted during the night. In all the mentioned houses, windows or openings were precisely done to allow the ventilation yet eliminate heat gain. Passive architecture is an approach to building design that uses building architecture to optimize building performance and improve occupant comfort. For this study, we explore different techniques such as wall thickness, roof insulation, glazing, and window-to-wall ratio. These techniques were chosen because of their relevance to the history of traditional houses of the UAE. Thick walls were commonly used to eliminate heat gains as air conditioning wasn't available, and roofs were always insulated using moistened palm fronds. As for windows and openings, their dimensions were perfect for ventilation while limiting heat gains. As for the progression of codes, in 2010, Dubai Green Building Regulations was issued to improve the performance of buildings in Dubai by reducing the overall consumption of resources, namely energy, water, and materials, which in turn will enhance the construction life cycle, beginning with the planning, designing, construction, and finally operating the facilities. Not only that, but its purpose extends to also enhance the public health, safety, and overall welfare to ensure that the city is providing the highest standards of comfort within the umbrella of sustainable living. Later in 2016, Al-Safad Green Building Rating System was launched. Al-Safad system enhances building users' safety and ensures a more sustainable environment for future generations. It also encourages innovation to achieve integration between green systems and technologies in the building design, which in turn is reflected in improving performance, reducing energy consumption, increasing the efficiency of electrical and mechanical systems, and therefore reducing the carbon footprint. Moving forward, the next part will be discussed by Hasan, where he will go through the result analysis and conclusion.
Results and analysis. To develop an understanding of the present scenario, the villa under study is simulated using the codes which were used during the construction period. As the villa was built during 2014 to 2011 to 2014, it was complying to the available green building regulations of Dubai at the time. Here is a snapshot of all the standards used in the development of the model. Once the model was developed, the simulation results were validated against the actual consumption of the villa. Upon validation, it was observed that there is a deviation of about 5.61%. That is, the simulated consumption is less by about 5.61% than the actual consumption of the villa. It is worth noting that the actual consumption of the villa is net meter. That is, the total consumption of the villa minus the total export from the solar power plant to the DEWA grid. Hence, to replicate the actual situation, the IES model has been developed considering the presence of an appropriately sized solar power plant. The calibration and validation is done with respect to the simulated net energy consumption only. To better understand the total consumption of the villa, the simulated consumption was broken down by end use. As the scope of the research is to study the effect of various passive architectural techniques, the breakdown of the total building consumption was obtained to identify the affected consumption. In this case, the selected passive architectural techniques will only affect the cooling consumption of the building. Hence, only that will be the scope of the study. The breakdown on the left shows about 64% of the total annual consumption of the villa goes towards cooling, while about 36% of the consumption goes towards non-cooling requirements. The chart on the right shows that the monthly consumption trend broken down into cooling and non-cooling consumptions. Once the base case was established and calibrated, we moved on to understand the consumption patterns of the platinum case, where the villa under study was simulated using the Al-Safad Platinum regulations. The table on the left shows the general requirements of Al-Safad Platinum Code, which were used for the simulations. The graph on the right shows the comparison between the actual consumption of the two cases. It was observed that there is a savings of about 6.9% in the Al-Safad Platinum case with respect to the Dubai Green Building Regulations base case. It is also interesting to see that there is a total savings of about 6.2% on the space cooling consumption itself. These savings are due to improvements in the operational efficiency as well as envelope characteristics in the Al-Safad code. In the coming slide, we will explore how much savings can be achieved by improving some of the envelope characteristics considered in the Al-Safat code. To explore the possibility of improving the insulation, we carried out simulations of the villa by assuming external wall U values. The experiment with the U values was conducted by keeping every other operational and design parameter same as in the previous cases and only altering the external wall insulation. The external wall of the house was assumed to be in three layers, that is, outer face, brick, insulation and inner face configuration showed in the figure. The various U values were simulated by altering the thickness of insulation. 6 cases with different insulation thicknesses and U values were simulated. The thickness was varied from 53 mm to 220 mm. The results of various cases have been summarized in the table on the screen. As we can see, the maximum savings which was observed at 220 mm thickness of insulation corresponding to insulation of U value 0.1099 watt per meter square Kelvin. The platinum case has been highlighted in dark in this table, which is being used as a reference for calculating the. To better understand the savings trend in cooling consumption, a simple linear relationship was developed between the external wall U values and the simulated cooling consumption. The figure on the left plots the cooling consumption as a function of the external wall U values. From the graph, it is visible that there is a strong linear relationship between the cooling consumption and the external wall U values. The cooling consumption can be calculated as a function of external wall U values using the equation on the screen. From the equation, we can then calculate the maximum possible savings, assuming the U value to be 0, that is, the external wall to be perfectly insulated. In case of the villa under analysis, the maximum possible cooling consumption savings that can be achieved hypothetically is of about 1.455%. To capture the effect of roof insulation on the cooling consumption, 5 cases were simulated by changing the U values and keeping the rest of the design operational assumptions same. As in the case of external walls, the structure of the roof was assumed to be similar to the locally prevalent roofing structure, that is, having an insulation outside, concrete slab inside, and a particle board later. For the experimentation, the insulation thicknesses which were simulated were from 85 mm to 275 mm. The platinum case has been highlighted in dark green in the table, which has been used as a reference for calculating the savings. Again, a strong linear relationship was observed between the cooling consumption and the roof U values. The cooling consumption can be calculated as a function of the U values using the equation on the screen. From the equation, the maximum possible savings can then be calculated by assuming the U value to be 0, that is, the roof to be perfectly insulated. In this case, the maximum possible cooling consumption savings that can be achieved hypothetically is of about 0.489%. Just like the experiments that were carried out for the roof and external wall U values, in this section we'll try to establish a relationship between the various glazing options and the cooling consumption. In the case of glazing, the gas within the cavity of the double glazed pane was changed to get various window U values. The experiment covered single glazed, double glazed with SVF, double glazed with air, double glazed with argon, and double glazed with CO2. The platinum case has been highlighted in dark green in the table, which has been used as a reference for calculating savings. As expected, a strong linear relationship between the cooling consumption and the glazing U values is observed. The cooling consumption can be calculated as a function of the glazing U values using the equation on the screen. From the equation, maximum possible savings can be calculated by assuming the U values to be 0, that is, the glazing to be perfectly insulated. In this case, the maximum possible cooling consumption savings that can be achieved hypothetically is of about 0.456%. Exploring further, the villa was also simulated using various window to wall ratios ranging from 15% to 40%. It is worth noting that the current building is already having a window to wall ratio of 15%. Hence, for the purpose of experimentation, the window to wall ratios were increased. From the simulation data, a relationship between the window cooling consumption and the window to wall ratio in percentage was established. The same has been mentioned on the screen. In this case, the maximum savings which can be achieved were calculated at 10% window to wall ratio, which is about 3.57%. To explore a compiled potential, a model with best configurations identified during the experimentation was simulated. Maximum savings achieved in the best case over Al-Safat was of about 1.514%. while the maximum savings achieved over DGBR was of about 7.643% in the cooling consumption. Even at a building level, similar savings were translated, as the experimentation of the passive architectural techniques only affected cooling consumption. Conclusion: historically, passive architecture was more about occupant comfort, as there was no building operational energy. With the development and advent of mechanical ventilation and cooling, the passive architecture has become about improving building comfort as well as operational energy. In 2011, Dubai municipality published the Dubai Green Building Regulations. This helped in ensuring that better built and operational efficiency practices are followed across the building construction sector. From the reviewed literature, it was found that DGBR could save up to 20% of energy with respect to conventional villas. From our analysis, Al Safad could help us save about 7% over DGBR, specifically to our case. More savings could be achieved, as in this particular case, the base case building, that is the building with DGBR, already had a solar photovoltaic plant. From the experimentations, we have established that there isn't a huge scope of improvement over the Al Safad Platinum case, specifically in the case of the villa under study. The reasons for low savings can be clustered grouping of the villas in the sustainable city area or the overall compact footprint of the sustainable city villas. Both of these factors have been considered in the simulations. Other villas with larger exposed area and individual standing design configurations might have a higher scope. The study also tells us that in the future, the scope for improvement in passive architectural techniques might be limited, and it is also very crucial to focus on the operational energy efficiency of the building. With this, we would like to end the presentation. Thank you for your time.